So because of a call, the recording stopped. So let's continue from where we got disconnected. So you see, that is how we represent the 10 in decimal number system, then 10 in binary number system, and then 10 in BCD. So this is how the same decimal number is represented in different coding styles: binary, BCD, so on and so forth. Now let us try to represent a given number in some other weighted codes, some other weighted BCD codes. So let us try to particularly write the code for a particular number, a particular decimal digit in 2421 code. So in 2421 code, if I pick randomly, let's say 2. So 2 in decimal number system I want to represent, so it is same, so no need to show this particular number because the weight will be same. Let us say this number. So 5 is represented differently in this particular system from 28421. So let me pick as 5 as an example, because 2 will be exactly same as the earlier one. So although we can see that as well, but we will more concentrate on this. So let me first explain you the 2 itself. So what we will do again is starting from the LSB, not from the MSB side. We will start from the LSB side, and we will multiply the place value with this is the face value, so multiply the face value with the place value of the coding style, coding this particular our method. So this is the code weights and this is the place value. So how this particular number, this particular code word represents 2? So let us see that. So if I multiply 0 with 1, so then it will be 0 into 1 is 0. If I want to represent 2, then this lower side one, whatever 2 is coming first, that should be represented as, that should be given as the weight 1. So if I want to represent 2, so this place will also get a bit 1. Then as whatever I wanted to represent, it has been represented by 1 0, so the further bits will be 0 0, should be 0 0. So this is how we represent. Now let us see how to represent 5. So I was talking about 5. So to represent 5, we will start again from the LSB side, not from the MSB side. Okay? Because the same word can be represented in this particular system, can be represented in 2 ways. But the one way will be wrong. So you see, if I try to represent the same 2 starting from here, not from the LSB side but from MSB side. So if I make this 1 and then 2 is 2 I got whatever I wanted to represent. So if I put 1 at this place, so rest of them will be 0. Then also this number will represent 2. But this is not the correct style. So to make it correct, you should start from the LSB, not from the MSB side. Okay. Same way, if I want to represent 5, so to represent 5 again, I will start from LSB side. So this place to represent 1, we have to make, see, this weight should be there, so 1, this should come, then 2, so if this will come, then it will be 2 plus 1, 3. Then to make 2 more is required, so this should be 0. So this is 0 and then this is also required. So you see, this is the 1 is coming at this place, at this the place value of this 2, then 0 at this place, then 1 at this place, and then 1 at this place. So if you multiply the place value with the face value of the code, then you get the decimal equivalent of that number. So this is how we represent 5 in 2421 code. Similarly, if we want to represent the number in some other coding style, BCD, other BCD code. So the other BCD code, I have taken example of 642-3 weight code. There can be other examples of this BCD codes, weighted codes. So there are many weighted codes, but I have taken these 3 weighted codes to explain you the method. Else you can understand it by any other codes also. So if I want to represent the number, any decimal number in 642 minus 3 coding style. Okay, 642 minus 3 code. Earlier it was 8421 code, then 2421 code. Now I want to represent a number in 642 minus 3 code. So how I will represent that? To represent that, any number, let's say I take the number 3. So to represent 3, what I will do, I'll start from LSB. So LSB is minus 3. So I represent this 1. Now you may ask that why we have not made this 0, this 6. You could have made them as 6 as well. But then see, 4 plus 2 is 6 and then minus 3. Could have made them as 6 as well. But we made this 6. Okay. So to represent any number in 642 minus 3, we can use the same this multiply the place value with the face value. Okay. Now to represent, let's say, I think there is some mistake in this particular code. So it should be 4 plus 2. So it should start from here. So 1, then it is minus 3, then 2, then 4. So some mistake probably I made. So it should be 110, I think. 110. Sorry, 111. This particular code I have not used at other place as well. So this should be the valid code. Rather than 1001, I think it should be 110. Sorry, 111. Okay, we should check it probably. If there is any correction, I will let you know. But for time being, it is looking to me that it should be 111. Okay, because as you may check it, that 11 is not used anywhere else. So this should come there, 111. You can check it from the book also. And if I made any mistake, you please bring that in my notice. I'll correct it. While writing the things, I might have made mistake in typing. So okay. Now let's say this particular codes, there is while doing the classifications, we saw that apart from the weighted codes, BCD codes are the examples of weighted codes. So apart from weighted codes, there is another classification which is called self-complementing code. So a code is called self-complementing if the code word satisfies what? If we take the 9's complement of a particular number and take the if we take the 1's or the 9's complement, if I take the 9's complement of a particular number and also take the 1's complement of that number, so I should get what? The complement of the number. So the complement of this should get, if we do the complement of this number, we should get the complement of this also. So if this is thing, then we call it self-complementing code. So this is what it is written here. If code word of 9's complement of n, so my n is, let's say, 3. So if I take the 9's complement of 3, so it will be 6. So see, this is what it means. So if code word of 9's complement of n, so if the code word of 3 the code word, the 9's complement of 3 will be 6. So 9's complement is 9 minus 3, so it is 6. So the code word of 9's the code word for the it is written, if code word of 9's complement of n is obtained by interchanging ones and zeros in the code word of n. Okay, so the code word of 3 is 00111. Okay, 0011. Now if I want to, this code will be called self-complementing if the complement of this, if the 9's complement of this number can be obtained by taking the 9's complement of this. So interchanging the ones by zeros and zeros by ones. So you see, the 9's complement of 3 is 6. Now you see, if I represent this every 0 by 1 and 1 by 0, if I replace 0 with 1 and 1 with 0 in this particular code, so do I get 6? If I get 6, then it will be called the self-complementing code. If I don't get this, then it won't be called a self-complementing code. So let's try this. So the code word of 3 is 0011 in 8421 code. Now I want to check whether 8421 code is a self-complementing code or not, depending upon this definition. So if I replace 0 by 1, so it will be 1, 1, 0, 0. If I replaced every 0 by 1 and 1 by 0. So now you see, if I do this, do I get 6 or something else? So if I do this 1, 1, 0, 0, it is not 6, it is coming as 12. So you can see very easily that 8421 code, as is not satisfying this particular thing, it is not a self-complementing code. Whereas if we check it for some other code, let's say 2421 code, so 2421 code. In 2421 code, if I represent 3, so it will be 0011. Now, if I again do the same thing, complement this particular number. So if I complement this number, so it will be 1100. So this is also the ones complement of that number. So the ones complement of this number is this. So the ones complement of the number is equivalent to the nines complement of the number. Okay. So if the ones complement of the number is equal to the nines complement of the number, then it is called the self-complementing code. If it is not so, then it will not be called a self-complementing code. So in this case 2421 code particularly, we can see that by complementing this the code word for 3, which we get as 1100, we get the complement of the nines complement of 3. So 2421 code is a self-complementing code. You can check it for the other codes also. So this is how we define the nines complement, the self-complementing codes. This is what the example I have taken. You can do it for some other examples also. We can take the example of let's say 8. So the 8 is the ones complement of 8 is ones complement of 8, nines complement of 8 will be 1. So if I complement this everything, so it will be 1110. So 1110 is exactly 8 represented in 2421 code. 8 is represented by 1110. So we can see very easily that 2421 code is a self-complementing code, whereas 8421 code is not a self-complementing code. Similarly, you can check for 642-3. Though I think I made some mistake here while writing this code 3, so I won't try this particular for this thing, but you can check it. Okay. But to me it looks like that. Let's try it for 1. So 1 is written as 101. So the nines complement of 1 will be how much? Will be 9's complement of 1. So it is 9 minus 1. So 8. So now 8. So it is, see how much it is coming. It is coming exactly the inverted of this. So okay, from this it is okay. But let's see. Let's check for 3. So 3 is this. So 9 minus 3 is 6. Okay. So this is coming like this. 0110. So this is looking correct to me then. Okay. Then let's check for 7. So 7 is the self-complementing, the nines complement of this particular code will be this nines complement of 7 will be 2. So 2 if I think, so then this particular code 642-3, as we can see that all the particular things are this particular, the nines complement of the number is representing the nines complement of this. So that is why this is also called the self-complementing code. So 642-3 is also self-complementing code, and the correct way to represent 3, that is why, because this is a self-complementing code, the correct way to represent 3 is this, and not what I have told you earlier. So it is not double 1 all the ones, but it will be 1001, because we want this code to be self-complementing code. So that is what the reason is. Okay. So I hope it is clear to you. So you correct whatever I have told you in the earlier this particular thing, in the beginning of the lecture, probably in the last part. Okay. Now one more important thing to note. So here it is, this is what I have told you earlier, that natural BCD is not a self-complementing code. Okay, natural BCD, or it is also called the BCD code. So whenever you refer the BCD, usually it is, we are talking about 8421 code. It should be very clear, it should be clearly talked, should be called as natural BCD, but it is very usual to call it BCD rather than the natural BCD. Okay, so our BCD code is not a complementing code. We don't use this 6421, 642-3 code and 2421 code very frequently, so we will not talk much about this codes, but 8421 is a very popular code, and this is used very, all the calculations everywhere we use this code. So, but while using this code, we should be very much again, we must be very much careful and should revise it once again, that there are 6 unused states or the illegal codes from 10 to 15. The codes, whatever you will get, there will be the illegal codes. So, if you want to represent any number from 10 to 15 in BCD, it should be of 8 bits, not of 4 bits. Binary number will be of 4 bits, but the BCD should be of 8 bits, because there will be 2 digits in the number, in the decimal number from 10 to 15. So for each digit, it will be represented by the group of 4 binary bits. So it should be very clear. Okay, now let's move on to the next slide and try to understand the arithmetic operations of natural BCD number. So we will understand this with the help of certain examples. So you see, let's try to perform the decimal addition in 8421 code. And why I am taking this 8421 code? Because this code is a sequential code, and in sequential codes, the sequential codes are the codes in which the consecutive, there is the difference of the next code is one higher than the previous code. It is not the cyclic code. In cyclic codes, there is 1 bit difference in the 2 consecutive codes, but in this sequential codes, we have the next code is 1 greater than the previous code. So this is what is important, and that is why these are useful for arithmetic operations. So we will try to see, and that is why we are seeing the arithmetic operations on this particular BCD code only. So let's try to perform this addition. So we want to add 679.6, which is in a decimal number, with this number, which is also decimal number. So I want to add these 2 numbers. So first I will add these numbers in decimal number system. We will get the answer, and then we will verify that how we will see the complete procedure, how to perform addition in BCD. If the number is represented in BCD, then how to perform the addition in BCD code, and then we will verify the result. So first we will add these 2 numbers. So if we add these 2 numbers, then you see 8 plus 6, starting from the, here we are starting from the LSB, okay, lowest significant digit. So if you are starting from the lowest significant digit here also in the BCD code we will start from the lowest significant digit, not from here, because you see in the addition process, as we already know from our schooling, that we should start from the lowest bit. So how we will start it, how we will add it in the, suppose these 2 numbers are in decimal number system. So how we will add them up? So to add them up, we will do 8 plus 6. So 8 plus 6 is 14. So 4 here and 1 is carryover. So 1 we will write here, then 1 plus 9 plus 6. So 9 plus 1 is 10, plus 6 is 16. So 16, 6 and 1 carry forward. So 1 plus 7 is 8. 8 plus 1 is 9. So 9 I have returned. Okay, there is no carry forward, so it is left out. Then 6 plus 5 is 11. So it is written here. So you see, this is how we add. Now the same type of procedure we will follow here also. But the only thing which we have to keep in mind is that, you see, here in decimal number system, we used all the symbols 0 to 9. So there is no illegal states. So we continue our addition, and whatever one we are this after adding 8 plus 6, we are getting 14. So it is actually 1.4. So 4 is here, we have written, and 1. Okay, then it is 9 plus 6 is 9 plus 1 is 10, and 10 plus 6 is 16. So 16. So we have written 6 here and 1 carry forward. Actually we are carry forwarding 10. Okay, so note this down. So 10, because then 1 is moving to the next higher place value. So if it is moving to the next higher place, it is becoming, the weight is increasing. So that we should keep into mind. So here also, if when we will perform the addition in BCD, so let's see that how we follow the same rules. So I'll first we should first start from the lowest significant digit. So let's see. While doing the example, we will understand the rules. So starting from the LSD, so you see, if I want to perform the addition of two numbers in BCD, first of all, I have to represent these two numbers in BCD. So let's say I want to represent this, I have to represent this 679.6 in BCD. So how I will represent it in BCD? So I will represent the 6 with a code word of 4-bit length. So 6 in BCD, if you see it from this table, so 6 in BCD is nothing but 0110. So you see, I have written 0110 here. 7 is nothing but, if you will see here, so 7 is 0111. So we have written 0111. Similarly, 9 is 1001. So 1001. Now 6 again, so 6 again is 0110 after decimal. So after point I have written 0110. Similarly for this code, so 5 is 0101. Then 1 is 0001. From the previous table you can check it. 6 is again 0110 and 8 is 1000. Now I have represented first of all the number in decimal number, the given number in decimal as equivalent in the BCD. So I have represent first the number in BCD correctly. So this should be correct. Okay. Then once the two numbers are represented in BCD correctly, then let's try to add them up. So how we will add them up? We'll start with this lowest significant digit. So the lowest significant digit, first group. So first group if I add, so I will see whether this first group is generating some carry or not. If the carry is generated but it remains within this group, then there will be something else. So let's see. So you see, if I add 0 plus 0, so 0, okay. Then 1 plus 0 is 1, okay. 1 plus 0 is 1, okay. I'll write it down. 0 plus 1 is 1. So you see, from this complete group, if I add this group to this group, no carry is generated, okay. So no carry is generated, so I have not used any carry in the next stage. If some carry would have been generated, I should write it in the next group, okay. But as this no carry is generated, so I will write it here itself, right. But the problem with this thing is something else, so I'll come to that, okay. I'll come to that later. But this is what the answer we are getting after the adding these two bits. This is not the final answer. This is the addition of this digits, last digits. Okay. Now let's move on to the next code. Code for this next digit. So next digit is this one, 1001. So if I add them up, again I can see that there is no carry is generated, no carry forward from this group to this group. Okay, no problem. So if there is no carry forward, then write as it is, whatever you are getting. Now in this case, again you will see that if you add this to this one, the answer will be 1000. Okay. Why I have written it in green, I will tell you later on, but let us see this. So again there is no carry is generated, so we'll write it as it is. Now adding this, again there is no carry, so okay, we'll write it like this. From this group, whole group, okay, so no carry is generated. There may be carry within the group itself, but there is no carry from the group. Outside, I mean, the carry is not moving from one group to the another group. So we will leave those things as it is. Now you see, if we got this as the answer, but this is not the correct answer. If I convert this thing into the decimal equivalent, what I will get for this decimal equivalent? See, 1001, 1011. Is there any BCD code for, if the BCD code is 1011, then is this a legal code or an illegal code? We have to first check this. So you see, 1011. If you will check from our earlier table, you will see that we have not used 1 0 1 1 for any of the representation. So we have code for from 0 to all zeros to 1 0 0 1, but we don't have code for this particular thing 1 0 1 1. So now this particular code is an illegal code. So the condition arises that whenever there is an illegal code, then we should add the illegal code, add 6 to the illegal code. Okay, if after performing the addition we get an illegal code, so that illegal code should be further added with 6. Why this is so? Because this is an illegal code and this is not allowed. So it will be from 11 to 15, and if I want to skip to the legal code, then it will be 6 bits, 6 states away. So that is why I am adding 6 here to skip the illegal states. That is what the reason. Okay, so you see, this is why I have added this. So wherever there is an illegal code, I will add this 6 to skip the illegal states, right? That is what the reason is. Now why I have shown this in green? The reason is this code is a valid code. Okay, this 1000, if you see, it is equivalent to 8. So this is not an illegal code. So we have not added anything to it. Okay, so this should be noted down. Okay, now this is also illegal code in BCD, and this is also an illegal code in BCD. So every illegal code, to every illegal code we add 0110. Okay, 6 to skip the illegal states. The reason is that. Now let's add them up and then see what happens. Again, if there is anything, if there is no carry forward from the group after performing this addition, then we will see whether the answer is a legal state or a illegal state. If it is a legal state, then we will directly note it down. If it is an illegal state, then again we will add 6 to it. Okay, so let us see. This is what we follow the procedure. This is what we have to do. So let's see. If I add, see, this is 6 we have added to all the illegal states. So after performing this addition, what I get is, so 6 is added. So after performing this addition, this is 0. So 1 plus 1 is 1 0. So 0. Then 1 plus 1 plus 1 from the previous state. So 3 ones. So 1. Okay. Then 1 1. So 1 is 1. Then 1 is written here. So carry forward. 1 plus 1 is 1 0. So you see 1 0. Now as there cannot be more than 4 the group of 4 bits, but in this after performing the addition we are getting 5 bits. So we will say that this bit is the carry forward bit. So we will move this bit to the next group, right? So this should also be clear to you. So we will note this down. So we will see this. Okay, so this particular thing will remain here only, whereas this will move to the next state. So we have carry forwarded it to the next group. Now again we will add 1 1 to this group. So after performing the addition, we get as 1 0 1 0 1. Now we will add this one from the previous state to this. So after performing this addition, we get something. So this something again we will see. So okay, we'll see, add 1 to it. So we'll see again, we'll come to later on. Okay, so now again this group generates 1 as a carry forward for the next group. So this will be moved, this one is moved to the next group. Again we will see, we'll add this. So we have added them up. Okay, so we see that this is 1001. Now this group is not generating any carry forward. So there is no carries moving from this group to this group. So we'll leave it here only. Now this group, as we have added them up, so this group has already generated a carry previously. Okay, because 1011 plus 00110. So this will give you 10001. Okay, so this is your carry forward. So now this cannot be moved to the next group. So this will be returned, but this will be returned in the BCD code. So this is one moved from this to the next group. So this one is written here. In the BCD, this one will be 0001. So we'll write it like this. Now this 001, which is left after this moving the carry, then what we get is this. So this we check whether this is a valid state or not. If this is valid state, we will keep it as it is and won't do any further step. But if it is an illegal state, then we again have to add 6 to it to skip the illegal state. That is what the reason is. Okay. This is also legal. So this is also a legal code. 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 And furthermore, after the decimal point, we can see that this is also a legal code. So we can see that all the this code words in this answer now are legal codes. So we will represent each of them with a equivalent decimal number, and we see that the answer is matching with our decimal answer. So we verify that this is our correct sum. So this is how to perform the addition of two numbers in BCD. Okay, so this is how to perform the addition in BCD. Let's see the arithmetic operation now in the subtraction. Okay, so we have seen here how to perform the addition of two BCD numbers, two numbers in the BCD code. Now let's see how to perform the addition in subtraction of two numbers in BCD code. So you see, to perform this subtraction in BCD code, again the steps are written here. So start from the LSD. In the previous slide I might have forgot to include these steps, but I have explained them very clearly, so no need to be confused with anything. So now let's see the same thing, the subtraction with these steps. So you see, we have to again start from the LSD. So these are the steps. In subtraction, in addition, what we have done, the carry was moved to the next step. But in subtraction, we borrow from the next state. Okay, so in addition, the carry moves to the next state, but here we borrows from the this next state. Okay, next higher state. So we will make the rules for that, and then we will see how to perform it, the subtraction, with the help of an example. So again here we will start from the last significant digit, first thing. Then if nothing is borrowed, then there can be only two possibilities. You may have to borrow, or you may don't need to borrow. If the number which need to be subtracted is smaller than the number from which it has to be subtracted, then there is no borrow is required. Okay, so no borrow will be required in such a case. But if the number which you want to subtract is greater than the number from which it has to be subtracted, then in that case you will require borrow. So in such cases, I mean, there are only two possibilities. You may require borrow, you may require to borrow, or you may not require to borrow. So if you don't require to borrow, nothing is borrowed from the next higher group, then no correction is required. Okay, it is very simple. But if there is a borrow from the next group, then 6 is subtracted from the difference term. Okay, so this is again to skip the illegal terms. That is what the reason is. The reason is same. In the previous case, when we have performed addition, we have added 6. Here in this subtraction, we will subtract 6 if it is an illegal code, or if it is this borrow has taken. Okay, if we have taken the borrow. So let's try it. Let's try to understand it with the help of an example. So perform the following subtraction in 8421 code. So how to perform the subtraction? So the number is 206.7 minus 147.8. So I want to subtract this 147.8 from 206.7. So how to do it? Let us first see it in the usual decimal number. So if I subtract it in the usual decimal number, you can use your calculator, or like here only you can understand it. So 7 minus 8. 7 is as smaller than 8, we need to borrow it. Borrow something from here, from the next higher state. So if I borrow, it will become 17. So 10 I am borrowing. Okay, that should be very clear. So 10. 17 minus 8 is now 9. Now here 5 is remaining. So 5 is again smaller than this, so I have to borrow from here. But this digit is again 0. So nothing can be borrowed from 0. So I have to borrow from the next higher state. So this will become 16. This will become 9, because you see this 1 will come from here to here. So it will be 1 0. Then this 1 0 From what this 10 you will borrow again 1, so this will become 9. Now 16. So 16 minus 7 is your how much? Oh sorry, and this is 15 because you have borrowed already 1 from here. So 15 minus 7. So 15 minus 7 is 8. Right? So 15 minus 7, you have written 8 here. Now here it is 9. So 9 minus 4 is 5. Now this is 1. So 1 minus 1 is 0. So your correct answer is 58.9. If you subtract 147.8 from 206.7, the answer should be 58.9. Now, if we want to do this everything in BCD, so how to do it? So in BCD, if you want to perform the subtraction in BCD, we have to first represent the number in BCD. We have to write the number in BCD. So to write the number in BCD, we'll write each digit, okay, in BCD, and then the whole word will be formed. So 2 in BCD will be 0, 0, 1, 0. 0 in BCD will be zeros, all zeros. 6 in BCD will be 0, 1, 1, 0. 7 in BCD will be 0, 1, 1, 1. You can verify it all the things from your previous table. Then for 1 it will be 0, 0, 1. For 4 it will be 0, 0, 1, 0, 0. 7 it will be 0, 1, 1, 1. 8 all 1, 0, 0. So this is the BCD for 147. This is the BCD for 206.7. Now let us see what we have to do. So as we can see that this is smaller than this, so we may require to borrow. Okay. So we may need to borrow. So if we are borrowing, then you see what is happening. So what we will do? We'll perform this subtraction. So if I subtract this from this, so what we'll do? We'll do this, and as we need to borrow, so we have subtracted 6 from it. Okay. Now